So my name is Mahmoud Moradi. I'm an assistant professor at the Department of Chemistry and Biochemistry, University of Arkansas. And I will be talking about some of the free energy calculation methods and some techniques and pathfinding algorithms that we have been developing currently when I was here at the Beckman Institute. And that was 2 years ago. And partly the stuff that I did after, and been continuing to collaborate with people here. And just recently we put a tutorial online in the tutorial website and this workshop website about some of the things that I'm going to talk about. So I only got to cover part of the things that we will cover today in the tutorial, but that's pretty much a good first version to do pretty much any kind of conformational sampling. And I will add more tutorials in the future to cover some of the things that we talk about here and are already implemented but are not available yet in the tutorial website or in the released form. So they are not basically documented yet, although they exist. People sometimes ask me to share, and I send them, and people have been using them, but if it's not documented, it's not officially existing. Yeah. So what we call the topic of this particular lecture that I'm going to give, that would be two kind of sections, but it's a continuation of the same thing, so it's actually just basically one. We'll cover part of it in the first session, and the rest next session. It's called Exploring Complex Reaction Pathways, or complex reaction or complex transition pathways. And the idea is basically to study the conformational changes, especially the larger scale conformational changes rather than local conformational changes of proteins, particularly membrane proteins. It is more general than membrane proteins. It's a general methodology, but the way that I have been fine-tuning the methodology is kind of more towards the membrane proteins. And it's been applied to several different, maybe now, something like 7, 8 different membrane transport proteins and other membrane proteins. And it's the same methodology that you can also find in the tutorial. So this is what I'm going to cover. First, I will just give an introduction that why we need this kind of methodology, which is not really an easy thing to do. Computationally, it's expensive. Methodologically, it's complicated. So why do we need that? So that's the starting point. And I will give you an example of the kind of simulations that people do for studying things like membrane transport proteins. And we'll see that why they are flawed and why we need to do all this craziness. Then I'll talk about the methodology, so the majority of my discussions will be related to the methodology. And the methodology kind of has two different parts. The first part is mostly related to an empirical search for good pooling protocols. So it's different from maybe some of the other methods that you've heard from, because it's not really a method. It's more a framework for you to see how you should deal with a conformational transition in an empirical manner. That means that you have a certain number of tools in front of you, and you want to generate something that is a conformational transition pathway. How to do that in terms of how to know if you're doing good, or or this doesn't work. So the first part is basically related to just non-equilibrium pulling, SMD, non-equilibrium driven simulations. You can call them many different things. Basically it means that you push the system using certain collective variables that you design. You have the choice of designing these collective variables. You are given this set of so many different collective variables, and it's up to you to choose them and to push the system in any direction that you want. It's possible, it's available, it's an MD. Now, the question is how you want to do this. Are you just going to use RMSD and do targeted MD? Or maybe there are better things to do, and why they are better. So this is what we're going to do for the first part of the methodology. And the second part of the methodology is for the next step. Now, if you have generated an initial transition pathway that you think makes sense biologically, now you want to characterize this using more rigorous methods, because so far things are somewhat arbitrary. You can push the system any direction you want, but now you want to make sure that what you have is meaningful. So there are different ways of doing that. These enhanced sampling techniques that we've heard about, free energy calculation methods, string method. So how to combine these for larger scale conformational changes, especially if they are coupled also to some other things like the interaction of the protein with ligand. So how to use pathfinding algorithms and free energy calculation methods together, and probably in an iterative manner, to get reasonable free energies and pathways. So this is the second part. And all of this has a theoretical or mathematical underlying model. And towards the end, I'm going to talk about that. That is being also developed now in progress. And we'll see that we are not necessarily doing with all of these, we're not necessarily doing things correctly. So there are still a lot of issues that we need to deal with at the theoretical level, not just at the implementation level or practical level. There are actually issues in the theoretical level. Just having a general formula for free energy and say that, well, free energy is minus KBD log of probability, and then probability, you can get it from different sampling techniques. That's not enough. It actually turns out to be more complicated than that. And that's also something that we may cover, depending on the time. And the applications are going to be throughout the talk. So I won't talk about these things in vacuum. I will give examples at every moment. So this is kind of fused in the entire talk. So this is the outline of my talk for this morning. And I'm going to start with an example. That's why regular molecular dynamics is not good enough. So the particular systems that I will talk about as my applications, they're all membrane transport proteins, or most of them are membrane transporters, or active membrane transport proteins, and some of them might be membrane channels, basically. The channels are passive membrane transport proteins. So for transporters, there is a particular mechanism which is common among them, and that is called the alternating axis mechanism. So they alternate between an inward-facing state and an outward-facing state. And this is to make sure that basically they can transport the substrate against its concentration gradient. If they are open, like for instance, if something like this happens, that they are open to both sides at the same time, the substrate is going to follow its concentration gradient. There is no way that it can actually transport something against its concentration gradient. This mechanism, which when you combine it with a substrate, at least you need one, usually there are more, then you have at least 4 states then. You have an inward-facing open, and then you also have an inward-facing bound, and you have an outward-facing open for the apoprotein, and also you have one which is bound. So, and these are not necessarily the same conformation. So we should never assume that when you change something in the system, it keeps its own conformation. If something binds to it, the conformation changes. It might be a large conformational change or a not so large conformational change, but there is some conformational change. And you should consider that. You should always, yeah.
So when you say conformation change, is it like a global conformation change you're talking about, like, or just a local one?
It depends on the system. For the systems that I've dealt with in my life so far, I've never seen just a local conformation. It's always something global. It may not be a very large one, but there is something global, something about the orientation of the helices also changing, not just one side chain, you know. For channels, you can also have larger scale conformational changes and global conformational changes. Not necessarily, but many of them do. And but for channels, it is allowed to be open to both sides. But nonetheless, what matters is that global conformational changes happen, and we need to characterize them if we want to understand the mechanisms. Now, the problem with global conformational changes is it's difficult to characterize them, both experimentally and computationally. So, I've been doing enhanced sampling techniques for a long time, but recently I decided to do just some regular equilibrium simulations. And I recently published a paper which is only based on equilibrium simulations, and this is the first time that I do this in my life. But it was interesting. So we simulated a particular transporter called GK-POD, which is a proton oligopeptide transporter, belongs to the POD family. You model it, put it in the membrane, and it's a proton-coupled one, so you want to kind of simulate this in different conditions, like when the proton is bound to the putative binding side of proton, when the substrate is bound, and different substrates, because it has different affinities to different substrates. So you want to try different conditions, and we did 8 different conditions, 4 with the proton, 4 without the proton, and then we had 3 different substrates, dialanine, diglutamate, and diphenylalanine. So different conditions. And we ran 2 copies of each simulation for 400 nanoseconds each. So a typical kind of molecular dynamics study these days. And that's the typical methodology used for most of these proteins if you look at the literature. So just get the protein, model it, simulate it in a couple of different conditions, look at the trajectory, and do some analysis, and then make some statements about the mechanism. So that's the common approach. And I would actually say that this is probably even more extensive than most other simulation studies that you see, especially if they come in with the experimental papers. When you do the experiment, you do a couple of simulations input there, so you have also done computational study. So what happened? We analyzed it. We defined a couple of different things: global variables and local variables. Like global variables. So the kind of the orientational angle between 2 different domains, the N domain and C domain, the N bundle domain and C bundle domain of protein. This is of course very important, because if it's going to undergo the inward facing to outward facing conformational change, it should have to do with this angle. This should change. especially this is part of the MFS family, and they are kind of suggested to follow the rocker switch mechanism, which kind of looks like a rocker switch. Other things, the orientational angle of certain helices that again we think play a role, like the angle between these two helices, H1 and H7, and the angle between these two helices, H5 and H11. These are global variables. And there are also, or maybe this one, the distance between two loops. And I picked this one because it's actually more common. Usually people look at the distances of the loops because it's just the center of mass distance and it's easy to do. So you don't need to, have a very good knowledge of VMD to be able to calculate the distance of two loops. That's why this is the typical way of doing it. So we do this too. And some more maybe local things like the salt bridge distance and a lot of other things. So we did a bunch of different global and local variables, and we monitored them. Let's see what we do. So for local variables, it's typically, if you have run a few hundred nanoseconds, seems to be good. Seems to be okay. So you see some consistent behavior, like this is the unprotonated simulation for this particular residue, and this is the protonated one. This is both for the apo protein, and these are for the substrate bound, the dialanine bound protein. So when it's unprotonated, the salt bridge, this is the salt bridge distance between the two particular residues that should stable within 400 nanoseconds. And when it's protonated, the salt bridge is not stable. Yeah.
How do you explain those peaks in between? Like on the top one, on the left side.
On the left.
Yeah.
You mean
these peaks? Yeah.
Yeah, it happens. It's a stable salt bridge, but the stability is a relative thing. So depending on the free energy, if it's 2 kcal per mole, you have more of these. If it's 4 kcal per mole, you have less of them. And if it's 8 kcal per mole, you have probably none of these. So it's different stability. Even here, it's pretty much stable, but it's less stable than there. So energetically speaking, it's understood. And then you can see that basically there is a difference between protonated and unprotonated. So locally, things are okay, typically. But what about global conformational changes? So here I'm showing the CN bundle interdomain angle that I showed here. So this is this particular angle from the principal axis, the third principal axis of each bundle. And then you look at the angle between them. So unprotonated apo, protonated dialanine bound. So you have two different conditions. And you look at the angle, and they both start from the crystal structure. Hard to see, but they start basically from the same point. One of them kind of goes up, the other kind of goes down. Wow, we've discovered something about the mechanism of this protein. Or the loop. So this is the loop distance that I showed again. There's some difference. But what if we repeat the simulation, the exact same simulation? That's what we speak in. So it sounds very simple. It's very easy to check, right? But this was actually published in PNAS just a couple of years ago. The exact same protein, they ran it for 200 nanoseconds rather than 400 nanoseconds. They didn't repeat it, and they actually recorded this. So this is actually the loop distance, the same loop distance that I showed. They did it in 4 different conditions or 3 different conditions, something like that. And there are some differences. And should we take these differences seriously? Absolutely not. These are just some random changes. This is just thermal fluctuation. Yeah. This is randomness. So if you average over the different quantities like CN bundle domain, H5, H1 interdomain angle, and other things, so just average over the entire trajectory, or I don't know, the last half of the trajectory. something like that, for the two different copies of each simulation. And then look at the standard deviation. In 8 different conditions, protonated, unprotonated dialing, you see no significant difference between any of them. So within 400 nanosecond simulation, there is nothing to say about the mechanism, because the mechanism is when you want to know what happens when the proton binds, how the global conformation of the protein changes, or when the substrate binds. But you can't say anything based on this, because there is no significant difference statistically between the simulation results. All you see is just fluctuation. So this is how I see this. I think there is a big mistake here. If you want to run some equilibrium simulations around a basin, a free energy basin, and then based on that, you try to speculate about the transition to a far state. Here, if you do the simulation, most of the fluctuations are going to be in this direction. But the transition is actually going to be perpendicular to that. And this actually is more often, this happens more often than thought. So, and sometimes you don't get anything which has to do with your transition if you run a few hundred nanoseconds of simulations. If you are dealing with really large scale conformational changes, very slow conformational changes. So this was just an introduction to why we need this, and most of you probably know this already because you are here and you are trying to learn the enhanced sampling techniques and use them. And if you thought that you can just run some equilibrium simulations, you didn't need to be here. Okay. So about the particular protein that I showed you, what we really need to do is, if this is the inward-facing state that we have from the crystal structure, we need to have an outward-facing state. We need to actually have it, have the transition, study the transition, to be able to make statements about the transition. We cannot just look at this and then make statements about the transition to this. We have to have the actual transition. And especially if this doesn't, if this hasn't been crystallized, like in this case, you don't have, in the pot family, you don't have any outward-facing state. All the crystal structures of the pot transporters, they are all in the inward-facing state, which is a common thing. So, you know, a lot of channels, they are crystallized in their inactive state. A lot of transporters, they are all crystallized in the same state. So sometimes there are multiple conformations, but more than often, this is the situation that you have. And my talk is mostly dealing with this kind of situations.
How did you model the open state? Like, what information did you have beforehand to model the outward facing?
This talk is about that. Yeah. So, yeah, you should use whatever information that you have, and I will tell you about that. But then, what happens is you start from somewhere, you generate something, and whatever information that you have. In this case, the general idea is we have a rocker switch mechanism, so you want to open the transporter kind of like this. So the first thing that comes in mind, and that's actually the tutorial, so this is not the same protein tutorial, but very similar. And if you look at the tutorial, you'll see that the first idea that you try is, because of your knowledge of the system and the proposed mechanisms, you define kind of two bundles, just like the way I did, and then you try to impose rotational changes to those bundles. So that could be a good starting point. And then you'll see if it works or not. And I will talk about that. So once you see the transition, then you need to optimize it, make sure that it works, make sure that it actually gives you an inward-facing, an outward-facing state. In this case, just pushing the system from an inward-facing to an outward-facing looking state is not enough. You actually need to equilibrate it. So the first test for your protocol to be a good protocol is it actually does generate what you want. So if you use your protocol, you want to go to an outward-facing state, and it doesn't generate an outward-facing state, it's not a good protocol. It turns out it's not that easy to generate an outward-facing state. Why? Because if you equilibrate them, most of them just go back to the occluded state. They don't stay open. So it's very actually hard to generate an outward-facing state. And I don't know any enhanced sampling technique that is capable enough to generate an outward-facing state for you, just automatically. It hasn't been shown yet. I mean, there are a lot of methods out there, and people brag about them, but just pick a membrane transporter, use your methodology, and generate the other state which is stable. Doesn't go back to an occluded state. So that's why I think the very first step of any enhanced sampling techniques or any study of the conformational change is not that much about the enhanced sampling technique that you use. It's more about your knowledge of the system and your own hard work of putting a lot of time and thinking on how I should actually generate a pathway which makes sense. Because if you don't have an initial pathway, doesn't have to be a perfect pathway, could be far from equilibrium, but it should make sense. If you don't start from there, whatever enhanced sampling technique is going to use is not going to give you that initial pathway. It can optimize your pathway and it can give you free energies, but it cannot give you complex transition pathways. Because mathematically speaking, this is just a very, very hard problem to solve with any single enhanced sampling tool. So our knowledge is very important here. And maybe this whole process that I'm going to talk about can be automatized and can be put into some code with some particular, I don't know, data mining techniques or things like that. I don't know, but it's not done yet. And until then, if I want to study a protein, the first thing that I do, I take the protein, simulate it, and then try to generate these different pathways, but following certain rules. And I will talk about some of those rules. So this is, of course, just the initial pathway. But that's not enough. Just generating a pathway that looks good is not enough. You need to optimize that pathway, and there are actually good techniques for that. And you need to characterize that pathway thermodynamically. That means free energy calculations. And there are also good techniques for that. So there are a number of different strategies that people take. This is one type of a strategy that I talked about, I will talk about in this talk. Yeah.
Sorry, maybe you will answer this in this talk, but when you say you generate that conformation and traverse the pathway, how do you validate that's the correct structure for the outer facing, given there is no experimental?
Right. So basically, of course, eventually you need to experimentally validate that. Right. But that's after the free energy calculations and all the optimization. At this stage, I use whatever information that I have. Like in this case, the water density. So I count the number of water molecules in an equilibrium simulation. So what you see here, the brown one, is the water content of the lumen from an equilibrium simulation of the inward-facing state. And the black one is the water content of the lumen from an equilibrium simulation that I ran based on my outward-facing state. And basically, it is consistent with the alternating axis mechanism. I have a lot more waters here and no no water is here. So we can say that it's not accessible to, that the substrate cannot access the binding site from the inside, but it can from the outside. And that's basically one test. Yeah.
When you generate the outer facing state, you turn the two halves of the bundle against each other.
Yes. Yes.
How do you convince yourself to rotate helices against each other with the side chain?
I don't convince myself, and that's why we need all these relaxation and path optimization after that. So this is an initial stage to know that you have a good initial pathway, but I actually know for a fact that the side chains are not equilibrated enough. And that is exactly why I need to run more simulations after that. And basically I have a 3-stage methodology that you have it in the tutorial, and I will talk about it. This is the first stage. Second stage would be optimizing the pathway using a path-finding algorithm, which is string method in this case. So with that, you allow for relaxation of other degrees of freedom around your initial pathway. So you have an optimization process, a relaxation process for the other degrees of freedom. And finally, you do free energy calculations, and that also relaxes things further. So this is just the initial stage. And what I'm trying to say here is, you've heard about the string method here, and it's a very powerful method, but it does depend on the initial pathway. So maybe not for dialanine peptide, but for this protein, if you want to have a reasonable pathway from string method, you need to start with a reasonable pathway. So you cannot start with some weird pathway and get a reasonable pathway. That doesn't work. It only works for small systems when you don't have so many degrees of freedom. So that is the point. Now, I just wanted to show, just because we are kind of in the introductory remarks, I wanted to show some of different strategies that people have for dealing with the larger scale conformational changes. And you've seen these different methods, and I kind of categorized them in 4 different categories and used some analogy. I just think it's fun. So you can have long simulations, very powerful machines, like an Anton machine that I use it too, and it's perfect. But does it actually give you, can Anton generate a pathway for the transport that I showed you? It can't, because the time scales are still beyond the microsecond time scale. You can also have a lot of trajectories. You don't have to use Anton. You can just have a lot of smaller machines or nodes and put them together. So multiple copy simulations, and they have been used in many different contexts. Even you can think of replica exchange as a multiple copy algorithm, or many other techniques that are not even enhanced sampling. You just run all these parallel simulations, and then you analyze them, and then you decide which ones to kill and which ones to keep and which ones to duplicate and so on. Another technique, which is the one that I will focus more on, is biasing the system. So now there is a human involved, and the human decides where to push the system. And you can also make these things adaptive. So the adaptivity is always an important factor. But the idea that I have, and most of the algorithms that I will talk about in the second half of the lecture are related to, look more like this. So you have a human involved, who designs the simulations, decides what collective variables to choose, and how to generate an initial pathway. But that's not enough. Just generating an initial pathway and looking at it is not enough, because you need to relax this pathway and you need to characterize it. And for that, you need a multiple copy algorithm and an adaptive one. So this is the kind of the picture that I have for a good methodology. And the algorithms that we'll see in the second half of the lecture are going to be like this. So let me start our discussions of the methodology. And I will focus more on the first part, which is the empirical search for good pooling protocols. So some ideas about the free energy calculations in general that kind of led me to this point. First of all, you need dimensionality reduction, because free energy is not meaningful if you don't do a dimensionality reduction. What does that mean? That means that instead of working with all the atomic coordinates, you want to work with some less number of variables, generalized variables, like collective variables. Using collective variables is basically a traditional way of dimensionality reduction for your system, because instead of working with all the atomic positions, you're actually working with a few collective variables. There are also more maybe advanced and automatic techniques for generating this kind of variables that use formal dimensionality reduction techniques. So PCA is the simplest one. It doesn't necessarily generate something better than an intuitive collective variable that you do, but maybe if you use more advanced techniques that are not linear like PCA, maybe we get to a point that, yeah.
Are there examples where you can reduce the dimensionality, but it's still meaningful? Like if you have like a ton of variables, does that kind of bring down your results because you have found a nice simple model for it?
I'm not sure if I'm following the question. So, so you are saying that, yeah, can you repeat
If
that?
you can't find a small number of dimensions that describe your
If you
motions,
can't.
if you can't,
Right.
does that necessarily mean that it's a bad model?
Well, how do you understand it if you don't have a set of, if you don't have a low-dimensional space to look at, how do you actually understand the model at all to say if it's a good model or not?
I mean, well, what if you have like a whole bunch of like eigenvectors and stuff, and that's what you use as opposed to like
Yeah, that is dimensionality reduction. So you have basically you have these eigenvectors and eigenvalues, and you look at them. That's dimensionality
But
reduction.
if you still have like hundreds,
Yeah.
is that still be meaningful?
Well, if you have hundreds and you don't have any way of ordering them, sorting them, if you don't know which one is more important, it's still going to be difficult to say something. So, or you don't have a way of combining them. So, it is fine to have hundreds of collective variables. Actually, in the simulations that we typically run, we do use tens of collective variables, if not hundreds, and that is fine. But eventually, at least in the analysis part of it, when you get to the analysis, you need to project this onto a space which is understandable for humans. So eventually we do need a dimensionality reduction. That's just inevitable. I cannot think of any simulation study without using some sort of a dimensionality reduction at the end to understand something of the system. And again, the collective variables are one way of doing it in an ad hoc manner, using your intuition, or some general but ad hoc techniques. And there are also more formal dimensionality reduction techniques, and they can be used and they can be combined. And another, going back to your question, this is actually related to that. What if I do have a lot of collective variables or a lot of dimensions, like hundreds or 50 or 200, something like that, and I don't want to distinguish between them. I don't want to say this is more important than the other one. So another way of dimensionality reduction is to have a particular region in this big space to be the region of interest. The simplest case is when you have a one-dimensional curve in this space. So it is not a particular collective variable. You can have hundreds of them, but there is a particular pathway, there is a particular curve in this space. And you can think of that as your reaction coordinate or as your collective variable. So that is also another way of dimensionality reduction. But assuming that you have a reason for it, that this is the pathway or this is the curve that I want to study, and there is a good reason for it. For instance, this is the minimum free energy pathway. And because it's the minimum free energy pathway, this is the most likely transition pathway. And because of that, now I have reduced the dimensionality of the system. Although I still have a lot of collective variables or a lot of atomic coordinates, but I have reduced the dimensionality by focusing on one pathway. And maybe I don't have even an initial good pathway, but I can optimize it and reach that minimum free energy pathway. But I'm just putting all this in the context of dimensionality reduction. So if you look at all these different ideas, they are all related to the dimensionality reduction idea. And the latest one requires pathfinding. Because if you want to focus on one path, you better study the right path. You don't want to spend your time on the wrong path. And you need pathfinding algorithm for that. And again, because you don't want to waste your time on the wrong path, it is better to make all of this process iterative and make sure that whatever that you get at the end of each step of your simulation, each stage of your simulation, whether it's the initial stage when you make the initial path or when you do free energy calculations, you do pathfinding algorithms, at any step and a stage, you need to make sure that what you have makes sense. And if it doesn't make sense, and it happens a lot, you need to go back and redo things. So this is an important idea that I think is not mentioned and is not talked about as much as it should, and it happens all the time. Don't tell me that you pick your system and you simulate it, and the very first time that you do your free energy calculation or your pathfinding algorithm or whatever that you are doing, the very first time that you do that, you get a good answer and you publish it. A lot of times you just go back and back and forth. You just change things. You see that it doesn't work. You go back and it should be that way because the problems are just too difficult to know what to do with them a priori before you start anything. And maybe we should actually officialize that. Maybe this should be an official strategy that, yeah, we do this and we are proud of it. And I have actually developed some ideas about how to combine all this bad data to maybe make the next iteration of our simulations better. Maybe we don't need to just, throw them away. Maybe there is a way of combining them, although they are not necessarily good, but still using them in some fashion. So these are basically the same ideas that I talked about, just rephrasing them, and you can also find them in some of these papers. But the idea is basically, first of all, collective variable based. And more than anything, it's the system specificity of the collective variables that makes them great. So I think if you have a generic collective variable, like RMSD, radius of gyration, and you say that you can use radius of gyration for any system, that's just not going to work. So the great thing about collective variables is that they are system specific. You choose them. And you have the choice of selecting the right ones. So there are poor collective variables and there are good collective variables. And it's up to you how to choose the right ones. Because you have the option to do that. And the iterativity comes here as well. So you don't necessarily know what is the right collective variable. But if you run a simulation and you get a bad result, you know that maybe you didn't choose the right collective variable. Maybe you need to modify it. It also could be that you used the wrong force constant or used the wrong simulation time. These are also possible, but maybe you should wait to get a better convergence. These are all possibilities, but collective variable plays a very, very important role. And I've seen this personally, and a lot of other people, well, not necessarily a lot of other people, but some other people have also reported the same thing. I should have probably put the reference here, but there is a paper from the Shaw lab, and they have actually looked at several different enhanced sampling methods for a particular system that they had got the trajectory transition pathway from their equilibrium simulations. It wasn't, of course, a transporter, but it was something that you could see in an equilibrium simulation. And they had tried FMD, string method, a couple of different algorithms. It turns out that the technique doesn't matter as much as the collective variables and the way that you define your collective variables. Like, for instance, for a string method, if they just use all the C alpha atoms, they didn't get the right pathway. But if they selected certain C alpha atoms of the system for their string method, they get the right pathway. And the pathway is actually the same as what they get from SMD, from a simple SMD, if they choose a collective variable which is related to those particular atoms that are playing a crucial role. So if you know what atoms you should use for your collective variable, what are the important domains of the system, you get the right answer no matter if you're using SMD or string method. I'm not saying string method and SMD are the same thing or are equivalent. I'm just giving you an anecdotal evidence for the importance of collective variables. So if you know your system and you use the right collective variable, it's a lot more important than using the right enhanced sampling technique. So the sophistication of your enhanced sampling technique is not going to cover your ignorance about the system that you're working with. And this is the problem that we have, because especially if you are working on various systems, then the question really becomes, is there a common way of dealing with all these systems? So I think that if you are working on different systems, using this empirical approach and learning about them one by one may actually give you some ideas of how to deal with the same category of proteins or the same family of proteins. But I cannot think of a set of collective variables that can be used for any given system. And that is the system specificity of the collective variables that I think is an important factor about them. Once you have a number of collective variables, then you need to use a pooling protocol, steering protocol. And for that, again, you have a lot of options. So the simple ones are the force constants and the simulation time. But more important than that is how you combine your collective variables. Are you just linearly changing all of them, or you should use a different way of doing this, maybe in different order? So there are a lot of things that you can do, and don't think of trying everything. Because if you have 4 collective variables and you want to combine them in different ways, there are so many ways of combining them. So it has to be always iterative in a way that you run the simulation, you analyze it, you compare it with the previous ones, and then you decide what to do next. You cannot say that I'm going to try all the possible ways of combining these collective variables, because there are just so many. So this is the empirical element that I talk about. And the empirical element is a general thing about the simulation techniques, enhanced sampling techniques, but it's more pronounced in this particular pooling protocols. So when you are using pooling protocols, you need to use this in an empirical manner to improve the protocol that you are using. And you have a goal, by the way. So your goal is what I mentioned in the beginning, that you want to generate a good initial pathway so you can optimize it and characterize it. And a good initial pathway has certain qualities. One of them is your final state should be what you want. It should be, for instance, if you want an outward-facing state, it should be an outward-facing state, which is stable. So once you have this initial pathway, then you can do path optimization and free energy calculation. And the idea that I kind of promote here is along the path free energy calculation. So rather than coming up with one collective variable, which is very, very difficult to do, you can keep your space, your collective variable space, large, not too large, but maybe tens of collective variables, but choose one particular pathway to study. Initially, that pathway comes from all this empirical search that you do, but then the optimization of the pathway with string method or other pathfinding algorithms, and eventually free energy calculations along that pathway. And again, you can iterate over this. You can iterate over all these steps. For instance, between the free energy calculation and pathfinding. Maybe after you do your free energy calculations, and it has happened, you do your free energy calculations, it should actually follow certain rules. It should actually pass certain tests to be a good free energy profile. And one of them is the fact that your initial pathway that you get from, for instance, a string method or pathfinding algorithm is sampled with, for instance, an umbrella sampling type simulation. But if you analyze your data and you average over the unbiased conformations, of course, if you are restraining the simulation around the pathway, the biased samples are going to be around the pathway. But if you unbias the data, do you get the same picture that the initial pathway that you started with was the right pathway? The data that you have generated with your free energy calculations is usually more extensive about that pathway than the data you had prior to that. So if you do pathfinding algorithms, you get to a pathway, that's your final converged pathway, And then you do a lot of sampling around that in your free energy calculations. And that generates a lot more data. Now you have more data than you had before. Now you need to check and see, is it actually consistent with the initial picture that you had? Was this actually the minimum free energy pathway? The data tells you if this was the right minimum free energy pathway or not. And most of the time it's not. So after you do the free energy calculations, you realize that, well, you were a little off. So maybe that's fine, but maybe you can also iterate. Do another maybe string method with these conformations that are now relaxed more. So the more you progress in your simulations, these structures become more and more relaxed. And this is just because of all these time scales that are there. Again, for a small system, this may not be relevant, but for a large system, this is relevant. And as you continue these simulations, there are just newer things that happen. There are just events that happen that you didn't have them before. And it gives a hysteresis to all your calculations, which is, I believe, inevitable with any kind of enhanced sampling that you use with a large system, and there are so many degrees of freedom involved. And not all of these are related to your protein. Some of them are related to the water, some of them are related to the lipids. It's just sometime towards the end of your simulations, you've done all of this, you have characterized this pathway, you have sampled it. All of a sudden, a lipid comes and gets somewhere, which is mechanistically actually relevant, but we didn't know that before. Maybe now we should redo everything, because now we have captured something. Okay, so what I'm trying to say here is there is no guarantee that whatever that we do is going to be consistent. Maybe we should actually accept that. We should just come to some sort of a radical acceptance of the fact that free energy calculations are imperfect. And we have to deal with them. Maybe we should report them. We should say that, well, we did all of this, but at the end of our simulation, a lipid came in and changed everything. And we don't want to repeat this anymore because we don't have the resources. But let's learn about what we have done. Because it's possible, and it happens all the time. A tyrosine amino acid all of a sudden flips. And we didn't know anything about this tyrosine, but towards the end of simulation it flips. And it happens to be a mechanistically important event that we simply just did not observe before. Now the pathway completely changes. The initial pathway that we started with was the correct pathway with your tyrosine in a particular conformation. But now, if tyrosine is in a different conformation, your minimum free energy pathway is a different pathway. And it's a possibility, and I've seen this. I've seen exactly this event happening, a particular tyrosine moving, and then my substrate moving a little down and interacting with some other residues. And now I have a new outward-facing bound state, which is different from the initial outward-facing bound state that I had, and I thought was the right state. So this is all possible. And that's why we need to iterate. We need to go back and check everything and redo things. And this is kind of my three-stage scheme with these arrows that go back and forth. You define collective variables, you optimize your biasing protocol, then you have a good initial pathway, you optimize that initial pathway using a pathfinding algorithm, and then you do free energy calculation. But then you need to assess the sampling efficiency, also the consistency of the results. They should be self-consistent. And you may need to go back, and you may need to go back to the very first stage and define and add a new collective variable to it. For instance, you see that you have a lipid, and your lipid head group all of a sudden starts interacting after a while that you've done all of this in the middle of these free energy calculations, is interacting with a particular residue in your protein. Maybe now you can define a new collective variable to describe that and include that in your search and include that in your path optimization. And that's just an example, again, of one particular problem that I've seen. So we thought that we had everything right, but then all of a sudden the lipid came and started interacting with a particular residue, and after a while, the lipid was flipped because of the interaction with the protein. So it seems a very strange thing that the lipid flips, but it does happen. And if you ignore that, and if this protein is actually interacting with lipids occasionally and flips them, then it's probably something that you should consider that in your simulations. So there are so many events that can happen, and they happen on many different time scales. And there's always something beyond the time scale that you're simulating. On every single time scale, something is happening. So as you move beyond, nanoseconds to tens of nanoseconds, new things happen. As you go from tens to hundreds, again, new things happen. As you go from hundreds to microsecond level, again, new things happen. And I don't know how we can ergodically sample when we are dealing with a situation like this. So this is a three-stage strategy, again, put in a different format. So you have a particular transition you're interested in, you're defining your collective variable, you're pushing the system using a particular protocol, a particular set of collective variables, and you then optimize this empirically until you get to a point that then you run out of ideas. You do your optimization and things don't change much. Then you say, okay, we are ready for the next step. And that's when you do, for instance, a strain method with swarms of trajectories to optimize your pathway, and you do, for instance, bias exchange umbrella sampling to calculate your free energy. And these are examples of pathfinding methods and umbrella sampling, but these are the examples that are available in AMP. So, again, this could be all iterative. So the idea is use work as one way of distinguishing between good and bad protocols. It doesn't tell you everything, but it's one of the things that you can look at. So if you use a particular protocol and it results in 1,000 kcal per mole, it means that you don't have a good protocol. And often TMD, targeted MD, does that. So I've done this with several systems. When you use targeted MD, typically you get values like this for work. And it has implications when you run your next steps. If you get a large work, it is related, for instance, to the exchange rate between the windows in your umbrella sampling, or bias exchange umbrella sampling. There is a direct connection between the amount of work that you get from a non-equilibrium simulation and the exchange rate that you get in an umbrella sampling replica exchange type simulation. They are actually related to each other. Or the overlap between the windows. How many windows you need? It's related to the amount of work that you get. These are all related things. So if you start with a protocol that requires a lot of work, that means you also need to have a lot of replicas for your umbrella sampling simulation. And also, it means that you are far from equilibrium. What does that mean in terms of the string method? If your initial pathway is far from equilibrium, very far from equilibrium, because 1000 kcal per mole, the work that you get is related to the distance from equilibrium, so to speak. And if you have a very large work, that means that your string method is going to also converge very slowly. It has a long way to go. So these things are all related to each other. But it is very expensive to run a string method and find out when it converges. It is very difficult to run an umbrella sampling replica exchange simulation and see when it converges. What is very easy to do is to run a SMD simulation with your collective variables and see how much work you need for that. And whether or not the protocol generates the pathway that you want, the final state that you want. So this is not very expensive computationally. It is more labor intensive because you need to do this one by one and think about it every time. But it is not expensive computationally. So the more effort you put in this step to generate a good initial pathway, the faster the convergence of your other simulations, your string method and your umbrella sampling simulation is going to be. So I want to show a couple of examples before the end of the first session for this empirical approach of choosing collective variables, and this is the example that I published a couple of years ago for the GLP-PT, which is the homolog of the same protein that I showed initially, and it's an anti-porter, so it basically binds a phosphate and goes to the other state, and then binds a glycerol 3-phosphate and transports it against this gradient, concentration gradient. So again, we have only one state, the inward-facing state for GLPT. And we want to generate the outward-facing state. So this is the same example that we have in the tutorial. Although the part that is missing in the tutorial is the optimization of the protocols, because that's something up to you. So we have a couple of different protocols, but it typically takes 20, 30, 40, or maybe more protocols to try before you get to a good protocol. And in this case, this is exactly what we did. So what we were interested in was basically reconstructing the entire cycle, the 4 states that I showed initially, inward-facing, outward-facing, apo, and substrate bound. And we only have one state, so we want to kind of reconstruct this whole thing. And it's possible. The idea is this, about the energetics of this system. And this is the typical diagram, like schematic diagrams that you see. We want to go from schematic diagrams like this that you see to real free energy calculations of the same sort. So this is the idea. And I think it's actually possible now. It wasn't so much possible. It was just some drawing. But we can actually go from these drawings to actual calculations. So this is the part that I'm kind of interested in. You have a transition between inward and outward facing state, and then which is assumed to have a high energy barrier. So in the apo case, the transition is supposed to happen very, very slowly. but when there is a substrate involved, it facilitates the transition and brings down the barrier. So this is the only state that we have, and I'm going to focus on this part, which is for the APO simulations, and this is also what the tutorial is based on. And we want to generate the outward-facing state. So we start with many different protocols. I have just some examples of them here. You can start with RMSD, basically you're running targeted MD, and you generate something, but it's not stable. You can just rotate all 12 helices based on internal symmetries, the inverted repeat model. You can model this based on some ideas and then use some sort of a rotation of helices based on those ideas. That's actually what I started with first. I didn't think of, I thought that it should be something complicated, but then I realized that if I just rotate the two bundles, it works. So at this point, I had a conformation which was open to the extracellular side, to the periplasmic side, and it stayed open when I ran some equilibrium simulations. But then I started optimizing this. I just tried to use particular helices rather than the whole bundle. And it turned out that if you use two particular helices, helix 1 and 7, later we realized why, but initially I didn't know why. If you just rotate these two helices, you generate the outward-facing state and it stays open. And it turns out that's because of the salt bridge between them. So you break that salt bridge, and basically the inward-facing state is not stable anymore, and it actually stays open if you keep it open for a little bit. And again, you can look at the content, the water content, just to see whether or not this is an outward-facing state or not. So this is similar to the other figure that I showed you. You start with an inward-facing state and you end up with an outward-facing state. You can monitor the water content along the trajectory. Another system, so I'm just talking about the non-equilibrium pulling and how you can work with different collective variables and different protocols to generate to generate the unknown states. In this case, the protein had a crystal structure, a very, very low resolution one. We basically didn't have any side chains in the crystal structure. So we have this outward facing state, which is a better resolution. We do have the side chains in the crystal structure, and then we start all the simulations from here. There is an inward facing state, but it's kind of closed here. And then there is a very big open inward facing state. And we wanted to kind of see which one of them is relevant because it was questioned. Also, we wanted to know how the transition happens and all that. Again, if you run an equilibrium simulation, this is like 300 nanosecond, this is what you see. So this is the outward facing state, this is the inward facing open, and this is the inward facing closed state. Yeah?
Are these inward facing ones you solve, those solve just quantity, or these just have hypothesis?
That's a crystal structure, yeah. But it's a low resolution one, 4.7 angstrom. But we don't start any simulations with that. All the simulations start with this outward facing state, which is nucleotide bound. So we remove the nucleotide, and we expect this to go to the inward facing state. That's what it's assumed, that if this is nucleotide free, the resting state is the inward facing state. So we expect this to go from here to here or somewhere like that in an equilibrium simulation, because that's the downhill actually conformational change. But still downhill doesn't mean 100 nanoseconds. Actually, in 300 nanoseconds, nothing happens. This is the alpha beta space that is defined like this. So this is alpha, which is this angle, and this is beta, which is that angle, and these are the important angles. So nothing really changes. It doesn't even get close to any of these states. It even goes a little farther. And I have now run with a homolog of this system a 30 microsecond simulation, and still this is just struggling to go somewhere farther than this. So this is just very slow. Even the downhill conformational changes could be very slow. So I explored different pathways with just non-equilibrium pulling with SMD. And at some point I started trying different collective variables that I have defined here. Alpha, beta, gamma is the relative angle, relative orientation of these two nucleotide binding domains and the distance between these two domains, things like that. So it turns out that if you push these different collective variables in different orders, you get a consistent behavior in terms of the amount of work. So whenever that you are pushing alpha before beta, which means opening the intracellular side before the extracellular side, you need more work. When you do beta before alpha, before gamma, you need less work than that, but more work than pushing beta and gamma before alpha. You can kind of see an interesting behavior in terms of the way the order that you do. Maybe it's not easy to distinguish between beta and gamma to see which one we should do first. It's not an accurate method. It just works when it works. So sometimes you see a consistent behavior and it's reproducible. So if you repeat these simulations shorter, so it's hard to do 160 several times, but if you do even shorter simulations of these, still you see this behavior. And not in terms of the individual ones, but in terms of the whole category of alpha going before beta always requires more work than the other ones. So you can actually see consistent behavior. And if you see consistent behavior, it does tell you about the mechanism. Although you haven't characterized the free energies, but it does give you some information. But eventually, you want to pick the best pathway that you can generate. And in this particular case, the pathway was generated with a particular protocol. And first, you separated these NBDs, and then you closed this extracellular gate, and then you rotated these domains, and eventually, you opened this. So you can actually come up with a protocol which requires less work than other protocols. And I'm not saying this is a transition pathway. I'm just saying that this is an initial pathway that I can start my other simulations with. And if I wanted to use an automatic algorithm to get to this point, like a string method calculation in a collective variable space, I doubt if I could using a reasonable computational time. So because this is just using a different idea for exploring the conformational landscape. And these ideas don't exist in the string method algorithm. String method algorithm is a local optimizer. You are locally just moving things along their potential gradient or free energy gradient. Here, this is more than that. So you are kind of doing a global optimization because you are trying different pathways in this high-dimensional space. You are trying different pathways. You are exploring different parts of the pathway. And if you want to use a string method and you start from somewhere, like some particular pathway, you will probably find some better pathway close to it. But I doubt if it goes all the way from one part of the configuration space to another part of the configuration space. Yeah.
I just want to make a comment.
Yeah.
I have to react. Sorry. Because you're part of a paper that uses the string for pretty damn complicated pathway.
Yeah.
Maybe 80 years. But we seldom actually use string, out of the group.
Yeah, but where the initial pathway comes from.
Exactly. So
Exactly.
That's what I want to say.
Yeah.
So that's what we
Something
do.
other than a string method.
Yeah, exactly.
Yeah. Exactly.
We never do use string. string method out of the box. I mean,
Yeah.
you need to do something for it. But it's, I mean, I agree with you that if you just take string, I mean, chances are that you shoot in the dark.
Yeah, yeah, absolutely. I mean, that's the whole point. The whole point is before doing the optimization with string method, we need to think about it, where we should start with. We should have some idea and some reason that this is my initial pathway. Yeah.
If I may just say another thing, and that's actually more like an apology to the audience. I presented this thing. I showed you, take this linear pathway connecting the two bases for the alanine dipeptide. That was kind of an arbitrary choice, kind of intuitive choice. Let it be known that, I mean, if you go to the paper of David Chandler showing that the 5-side space is enough for our reaction coordinate. What he showed in that paper, that there are two other reaction pathways, also minimum frequency pathways. So it's kind of akin to what Mahmoud was saying, is that you have to make a decision, and that's where the intervention is necessary. In our case, a very simple case of dialanine, we made this choice, it's not a very choice for that in a straight line, but there are other pathways by virtue of periodicity of the binding site.
Yeah, thank you for the comments. And yeah, I mean, I'm an advocate of the string method myself, and I implemented the string method with the TCL scripting of NAMD, which is now available with the tutorial that I just put website, and that's what I will talk about in the next session. So string method is great. But it's only one piece of the puzzle. So before you do a string method, you need to generate a pathway. And there are different ways of doing that. So this is an example. And do I do this with all the systems that I do? No, actually, I only did this once. This particular type of this is very hard. So and it's a very complicated system. But if I want to do some system like this, like another ABC exporter, I would do this. I would basically use a protocol like this to start with. Now I've learned this about the ABC exporters. But the initial part is basically empirical. So you use ideas from different theories, like for instance in the paper that Chris was mentioning, we used some sort of a coarse graining for the initial pathway. So we started with an elastic network model type calculation to generate an initial pathway, and then from there you used some other steps to relax it further and so on. But the initial pathway has to come from somewhere, and some ways of doing generating the initial pathway are better than others. And there is a way of judging what is good and what is bad. And one of them is the work. So if you have an initial pathway that is generated by a non-equilibrium pulling SMD simulation, you can look at the work and see if the work makes sense or not. If it's a very big, large amount of work, then the chances are your string method is not going to converge very well or to a reasonable pathway, and your free energy calculations are not going to converge very well, and all.